Great, thank you very much, Neil, for that great overview of the project and the workshops and the richness of this data that you've been using. So next up, we have a response from Dr. Thomas Kjeldsen, who's a senior lecturer in engineering at the University of Bath. And I think he's going to show us a couple of slides to respond. So we'll get a different perspective now on some of the work that's been done. So over to you, Thomas.
Thank you. Can you see that?
Yeah, I can see that. Your camera's on. Yeah, all good.
Okay, yeah. So thank you, Neil. Yeah, so it was a great pleasure to be a part of this this workshop. I think I was the only engineer there, really, among all the participants. But that was interesting because engineering is very much a quantitative science rather than a qualitative science, so it's all well with these stories, but we have to have some hard numbers to make actual decisions with, and that's what we've been grappling a bit with. So I'm just going to talk through an example where we've tried to make use of some of all the things that were discussed in these workshops, and where the value of really bridging the quantitative and the qualitative data really came into play. So this is a sort of, this is example from a project that we've been working on, which involved architects, historical architects, civil engineers, and statisticians as well. And we've been trying to recreate the flood history, very much like Neil just described, at the River Avon in Bath over the last 200 or so years. So you might not be aware, but in the past, so pre-1960, Bath was very susceptible to flooding, frequent flooding, and quite destructive and costly flooding. But around 1960, it got so bad that lots of intervention was done. The river was changed, bridges were taken out, river channels were dredged and aligned to be more hydraulic efficient, so we could send the water through Bath down to our downstream neighbours quicker, thereby prevent flooding in Bath. So the typical situation, so Bath is just one example. This, Neil talked about the rivers in Manchester and in Scotland as well. The situation is the same in many places where cities are built on rivers, that we have a situation where we have the black dots on the right. So on this graph, we have time on the x-axis, years, and the peak flow of different flood events on the y-axis, so cubic meters per second. So this is the River Avon in Bath, and the black dots on the right are systematic measurements made by the Environment Agency and their predecessors, starting from about 1940 or so. And then the triangles on the left are flood events that were never formally recorded using gauging stations, but where we have deducted the flow based on evidence that has been left on buildings, bridges, in all this qualitative information that Neil talked about. So we tried to reconstruct these flood events. And the reason we're doing this type of work is because ultimately, as engineers, we want to create graphs like this, where on the x-axis we have the probability of flood events expressed as a return period, so the average amount of time you have to wait before you experience a flood like this. And then you have peak flow, again, magnitude of the floods on the y-axis. And this is very typical, so you have the black dots here, they are the sort of contemporary observations made by the Environment Agency. Given that we have about 40 to 60 years, that the return period of we can calculate based on these observations is really quite low. And if we want to predict things like the 100-year flood or even the 1,000-year floods, which are the sort of floods of that magnitude we need for planning and design purposes, that requires quite a lot of extrapolation from our observed short records into the future. And that extrapolation comes with a cost, and that cost is a large amount of uncertainty. So by using this historical data, by translating this qualitative information into quantitative data, in a way that allows us to add these historical data to the contemporary data has been shown to really restrict these prediction uncertainties. So we're much more sure that when we're building flood defenses, mapping the outline of the 100-year or the 1,000-year flood, that we are in the right ballpark if we support these type of analysis with historical data. But it's not a straightforward thing to do. So Neil talked about the different kinds of data, and often what we found was that the two data types, well, they both, the historical floods and the contemporary flood data are somewhat a bit like apple and oranges in some way. Because the historical flood marks represent the river as it was at the time these flood marks were left. And interestingly, when you look into the sort of qualitative story of flooding in the city, every time there's been a significant flood event, the city has changed. People have done something to change the city, to try to alleviate further flooding. And here's some examples. So on the top here, we have, for those of you familiar with Bath, we're looking from the train station, the back of the train station, looking at the river going down towards Bristol. On the right, this is what it looks like today. This is called Churchill Bridge. This is the bridge that connects the southern bit of the city to the city centre on the northern side. And it's basically an efficient slab of concrete that spans a river that has been, it's very geometrically defined and has a high, this is quite hydraulically smooth. Whereas if you went back there a few hundred years ago, you would see the picture on the left, which is called Old Bridge, which was a beautiful old stone arch bridge. But unfortunately, this arch bridge also acted as quite often acted as a dam, because it got blocked by timber and dead cattle, etc., coming from upstream of Bath. So as a result of the blockages from this bridge, the flood marks that the ancient flood marks that are left in the city are way higher than anything we would experience today. So the same amount of flow in 1800 would create a water level much higher than that flow would create today. So to try to make a coherent data set, we spent a lot of time going through quantitative and qualitative information with the aim of building a hydraulic model through the city representing the river and its environments in the 1800s. And this required going through a lot of qualitative information, lots of pictures of flood levels, especially where the floodplains might have existed back then, lots of newspaper accounts, trying to figure out where the flood levels would have gone in 1894, etc. Lots of old reports, engineering reports, and interestingly, the environment, we found a lot of this material stored away in the Environment Agency in an Environment Agency office in Bridgewater, not catalogued really, scanned and dropped in a online archive, unnamed. None of the 1,000 scanned pictures were named, so it took us a substantial amount of time to go through all this. But lo and behold, it took, after a year and a half of work, we've created this historical model, and we've been able to as I say, reconstruct the flood events, and we think this is the process of a good example of bridging the qualitative and the quantitative. And the aim, hopefully, will now be able to predict the 100-year flood on this river, and therefore also in nearby rivers with much greater degree of confidence than we could have done before. So I hope this is an example of why this is important work and how it might be put into use. So I'll end the presentation here.
Brilliant. Thank you very much, Thomas. That definitely puts the importance of this in a context, in a real practical context. So thank you. We're now going to move to Q&A.